So this is lecture 9, where we're going to talk about digitisation. So wherever you are joining us from, whether you're still in the UK or you've gone home, I hope you're all home, safe and happy. So it's a shame I can't see you in class today, but I'm trying my best to not make this an obstacle for you. So today we'll be talking about digitisation. So this is lecture 9. Before we start, let me say a few words about your class test, a little bit of feedback. So you all have your marks and you've seen the feedback. I've made a slight adjustment to the mark scheme, and as you can see, almost 50% of the class have scored marks between 70 and 100, with roughly, I think it's 11 students actually getting 100%. So that's really good. So half the class getting marks between 70 and 100 is really good. And an average of just under 71% again is really good. And a quarter of the class getting marks between 60 and 69 is also good. What's not so good is a small number of failures, but it seems that almost everybody in that category didn't actually take part in the practice test, so didn't do the practice test. So I put the practice tests online for a reason. It's to prepare you for the class test. So everybody else, so if you find yourself in one of these two columns, then think about what you need to do to bring your mark up into the 70s and 80s. So that it could mean more practice. It could mean closer attention to the lecture notes. It could mean going through the problem sheets in a little bit more detail. But really, even though I'm happy with the average of 70%, that's good. I'm happy with an average of 71%. You shouldn't be. You should always be trying to improve your marks further. Okay, in terms of the distribution of questions, I don't want to spend too much time on this, but according to Vital, out of the 63 questions, 53 Vital termed good in terms of discrimination. Vital thinks that 3 questions were poor in terms of discrimination, and the reason was because everybody who answered these questions got it right. So Vital says that's not a good question. So 7 were fair questions, so they were judged either too easy or too difficult. And in terms of difficulty, 27 questions were judged by Vital as being easy, 32 medium questions and 4 difficult questions. But these 4 difficult questions, nobody had all 4 questions in their test. So each of you will have had exactly 1 of these difficult questions in your test. So I've tried my best to make sure that the exam or the class test was fair and everybody had the same mix of easy and poor questions. Now that isn't it's never perfect, but all I can do is try my best. Now, before talking about the next assessment, let me just say a few words about where we are in the module. So we've spent 8 weeks talking about modulation, and analog modulation in particular. So we've spoken about all the different variants of AM, amplitude modulation, and the 2 variants of angle modulation. And for each of these, we've spoken about the bandwidth, or the spectra. We've spoken about power considerations, power efficiency. We've spoken about modulation and demodulation, whether it's a circuit or a block diagram. And we've spoken about the applications of each. We've also spoken about the advantages versus the disadvantages. of each. Okay? What we now want to do is take the next step and talk about digital. So digital communications, before we do that, before we can get started about different type of digital communication and what we do with digital signals, we need to get across the bridge, the gateway between analog and digital. And there are two steps to this. There's sampling and quantization. So sampling, you've seen this before, you're familiar with this, you've come across it at least in two places. You've come across it in ELEC202 signals and systems, and you've come across it in ELEC207, which is your instrumentation and control. But quantization, you may have come across this in instrumentation and control. It's referred to as ADC, analog to digital conversion. But we'll cover both of these in today's lecture so that the remainder of the module we can talk about different types of digital transmission. So where are we now? We are right here, and we have a few more lectures to go. One lecture on pulse modulation, 2 lectures on digital modulation, and a lecture on multiplexing. This is still there. I haven't cancelled that. So the class test still exists. It's on the 30th of April. So make sure that's in your diary. So put 30th of April in your diary. Okay, it's not a class test, it's a home test, but it's happening on the 30th of April. Okay, you'll be taking the test from the comfort of your own home, but it'll be a simultaneous open book home test. Simultaneous means you'll all be doing it at the same time. What's included? FM, PM, so that's lectures 7, 8, 9, 10, 11, and 12. Okay, so there might be 13 lectures, so the last lecture might not be included. I will make that very clear as we get closer to the actual test. So the intention is to have 15 questions in 1 hour. Now, that 1 hour, I might need to extend that because what I want to avoid is vital issues, connectivity issues, internet problems. So I want to make it as stress-free for you as possible. So I will try to make sure that the examination process is as smooth as possible. And the reason is I want you to get that 15% so that whatever happens with the exams, we still don't know what's happening with the exams. So your final exams, we still don't know. Okay? As soon as there's some clarity on that, I will share that with you. And I'm sure the head of department will get in touch. But until then, what I can control is this. Okay, I do know that we have 15% that you can work on yourself. So that class test will become a home test. So it's like a homework, but you all do it at the same time. Okay, I'm not going to make the questions any harder as a result of this change. It's the same questions. I will make sure that you have all the practice you need. So there will be a practice test. Okay, you will have a practice test, and I will make sure that the practice test will help you towards the home test. Okay, and there will be plenty of videos available on YouTube and plenty of questions in the problem sheets. So whatever your average from class test 1 is, try to improve it for class test 2. So try to shift your average up and get as much of that 15% as you can. If you have any questions about the class test, post those on the class test discussion board. So not the general discussion board, on the class test discussion board. And I'll address those in time. So today, as I said, we'll be talking about 2 things, sampling and quantization. Sampling you're familiar with, quantization you might not be. Now, why is digitization important? Digitization is important not necessarily for those reasons. These are well-known reasons. That's why digital communication is desirable. That's why we like digital communications. But if the original message, if the message itself is analog, such as my lecture today. So today, my lecture is analog, but it's arriving to you through digital means. So digitization is necessary in order to take this analog signal and to transmit it digitally. So it's traveling through a number of different components. It's going through my iPad and it's being digitized. It's being uploaded to the cloud. It's then traveling through different routes to arrive to you. But it's arriving as part of a digital package that is it's either a YouTube video or a lecture stream, or it's some kind of digital package with other digital content, such as this PowerPoint. Okay, so this PowerPoint is digital in origin. Why am I saying this? Because sampling and quantization, i.e. digitization, is not necessary for digital data. So when the data is digital in origin, so if you have, something like an email, that's digital in origin. Or if you have an image, that's digital in origin. It doesn't need to be digitized. That will just travel through the digital communication network normally. Digitization is important when the actual message is analog, not digital. Okay, so everything we're going to talk about today is about when the message is analog. That's why we need digitization. When the message is already digital, then it's already prepared, it's already suitable for digital transmission. So, sampling, what is it? It's converting a continuous time signal to a discrete time signal. Why can we do that? Because there's something called redundancy. What does that allow us to do? It allows us to reconstruct the signal at the receiver without having to transmit the whole message. So if my signal looked like that, then all I need to do is transmit these samples, and at the receiver, you would only have those samples. Yet from these samples, we can then reconstruct the original signal. So reconstruction is, if you like, the opposite of sampling. So you can think of sampling as a rapid switching process where you have some continuous time signal that then turns into a discrete time signal. And you're familiar with the concepts of undersampling and oversampling. Undersampling is where you don't have enough samples, and oversampling is where you have too many samples. So oversampling is a better problem to have than undersampling. Why is that? Because if you undersample, if you have fewer than 2 samples per cycle, then you're unable then to reconstruct the high frequency components of your original message. You might think that your original sine wave looked like that low frequency sine wave. So that's called an aliasing effect. Can we reverse that? Is it possible to reverse that? Can we undo that? Can we somehow take an undersampled signal and reconstruct the original? That's a question for you to consider, and we'll answer it in a minute. So back to this Nyquist criterion that you've often seen quoted. The Nyquist criterion says that the sampling rate needs to be at least twice the highest frequency component in the signal. Another way of saying that is saying that the time between your samples, the period between your adjacent samples, needs to be at most the reciprocal of twice the frequency, or twice the highest frequency. So your sampling rate needs to be greater than or equal to 2b, and your sampling period needs to be less than or equal 1 over TB. That's obviously for a band-limited signal. By band-limited, I mean a signal that has a finite bandwidth of FM. Actually, let's not call it FM for now. For this slide at least, let's call it B. So if you have a signal that is band-limited to B hertz, then your sampling rate needs to be at least twice B hertz. Now, if it isn't band-limited, if your signal has a spectrum like that extends to infinity, then we often need to artificially band-limit it by passing it through a band-pass filter. Sorry, a low-pass filter. So the low-pass filter will force the signal to become band-limited. So you're physically cutting out all the high-frequency components. Why would we need to do that? In order to be able to satisfy the sampling theorem. So, question for you. If you had a signal with two components, 1 kilohertz and 3 kilohertz, what's a suitable sampling rate? So, the Nyquist rate is twice the highest frequency. And the highest frequency is 3 kilohertz. We are not interested in the lower of the two frequencies. We don't care about the 1 kilohertz. So we're interested in the 3 kilohertz. Twice that is 6 kilohertz. But 6 kilohertz isn't a suitable sampling rate. It's still too low. That's critical sampling. Okay, so this is critical sampling, and that's not suitable when you have a sine wave. Clearly, anything less than the Nyquist rate isn't suitable. So an acceptable answer for this question would be 8 kilohertz. So 8 kilohertz is fine. Now 100 kilohertz, here we are oversampling. Now, even though we're also oversampling at 8 kilohertz, 8 kilohertz is a reasonable oversample. So 8 kilohertz, 10 kilohertz, even if you go up to 20 kilohertz, that's reasonable. When you get to 100 kilohertz, then you are seriously oversampling. So even though you could reconstruct your signal, sampling at 100 kilohertz, it's not a suitable, it's not an appropriate, it's not an appropriate sampling rate for a 3 kilohertz sine wave. This is a very similar question, but we're not asking for a suitable rate, we're asking for the Nyquist rate. So the Nyquist rate is twice the bandwidth. And the bandwidth isn't the difference between these two. Because it's a baseband signal, the bandwidth is the higher of the two frequencies. So we're talking about 2 times 3,300. So the answer is clearly 6,600 hertz. So this is an example of where, in order for our signal to be sampled, so this is our voice signal, you would need a filter to cut out all the bits that are above 3.3. So let's just put 3.3 there. So you would need a filter. In this case, the filter is in the form of the phone line. So the phone line acts as a bandpass filter. It cuts out the low frequencies, less than 300 hertz, even though there are components in the human voice. You can see them here. And it cuts out all the components above 3.3 kilohertz, even though there are components there. So these components are all cut out by the phone line. So if we wanted to sample, we would need to sample at a rate greater than twice that. So even though that's your Nyquist rate, your sampling rate would be something in the region of, maybe 10 to 30 kilohertz. Now, this, again, you will be familiar with. When you multiply a signal by a comb function in the time domain, it's the equivalent of a convolution in the frequency domain. And here you have a band-limited signal, and the same band-limited signal, same spectrum, is being replicated an infinite number of times. It's not just at 0 and fs, it's an infinite number of times. And to be accurate, this should be frequency in hertz rather than omega. So that's replicated an infinite number of times. And here is just an illustration of the three scenarios where you have critical sampling, oversampling, and undersampling. So undersampling gives you this overlap, which results in a spectrum that might look like this because you're adding the two spectra, whereas oversampling gives you this convenient transition band or guard band between your replicas, and that allows you to apply a low-pass filter that might not be ideal. Whereas for critical sampling, your low-pass filter would have to be a brick wall ideal filter. If you didn't have a brick wall filter, then it wouldn't be possible to reconstruct your original signal even if you were critically sampling. So, to recover, you would need a low-pass filter. So a low-pass filter, we've come across a low-pass filter twice today, once in the form of an anti-aliasing filter and once in terms of recovery. So, if you oversample a signal, that means if you sample at a rate greater than the Nyquist rate, can you perfectly reconstruct your signals? I think we're all happy with that answer. It is absolutely possible, in theory, to reconstruct the signal perfectly, provided we have the necessary recovery circuit. Now, we've spoken about aliasing and how if the samples are too far apart or if the sampling rate is too low, then we have some form of distortion. We've looked at that in the time domain, we've looked at that in the frequency domain, but is it possible to avoid aliasing or to avoid the effects of aliasing? So there's this term called anti-aliasing. And an anti-aliasing filter can either be a pre-filter or a post-filter. So what does that mean? That means that if you have your sampling and you're not able to sample at the Nyquist rate, for whatever reason, your clock, your sample rate cannot exceed the Nyquist rate, you're going to end up with aliasing. So you have a choice of having a filter before or a filter after your sampling. And I say you have a choice, sometimes you don't have a choice. Sometimes that choice isn't yours. But it is possible to filter before sampling sometimes. It's sometimes necessary to filter after sampling. And that gives us this idea of a pre-filter and a post-filter. So, which is better? Is it better to filter before or after? So think about that. Let me give you a little illustration. If you had a signal with a spectrum like that, say it was band limited to B hertz, and let's say you were unable to sample at twice B, so critical sampling would give you a spectrum like that. But let's say you were unable to critically sample. Let's say your sample rate was limited and you sampled at something only slightly greater than B. So you would end up losing a lot of, let me draw it a bit better. So let's say that's B, and let's say you're sampling at a rate greater than B, but less than 2B. So you end up with overlapping spectra. That is what we refer to as aliasing. So this is your spectral overlap. That's no good. We want to avoid that. Two things we can do. We can either filter the signal before sampling. So if we apply a low-pass filter before sampling with a cutoff frequency there, that would allow only this much of the signal to actually go into the sampler. So our sampling would actually become a critical sampling. So what you would have is critical sampling, and your replicas wouldn't actually overlap. They would look something like that. Now, what we've done is we've avoided aliasing. So we have successfully avoided aliasing. We haven't reversed aliasing because aliasing hasn't happened. But this has come at a cost. What's the cost? We've lost this much of the signal's bandwidth. So this bit of the bandwidth is lost forever. So it's not all good. So sampling or filtering before sampling isn't necessarily a solution. It's not going to avoid the distortion, because we're losing some of the bandwidth. But it's better than the alternative, because if we didn't filter before, if we filtered after, then we would have lost all of this. We would have lost all this frequency band, which is considerably greater than this band here that we would have lost if we were to have filtered before. So it's always better to apply your filter before sampling. Obviously, it would be better not to have that problem, so we would sample at a rate greater than the Nyquist rate, but if we're not able to do that, then a pre-filter is better than a post-filter. So we're talking about pre-filtering. A pre-filter is better than a post-filter. So this is the same idea. So pre-filtering is better than post-filtering. So even though what we've done is we've converted our signal from discrete time to from continuous time to discrete time, it's still not digital, it's still analog. We still need to convert it into discrete amplitude. So this first process, this is the process called sampling. The second process is the process of quantization. And that's the remainder of today's lecture. So here our signal is analog. Here our signal is analog. And only here is our signal digital. So our signal is digital only after quantization. So the red signal here is our digital signal. So imagine if we're not looking, we're only looking at the discrete part of the red signal. So it's joined up in the way it's illustrated, but in reality it will be discrete. So don't worry too much about this block diagram. We're interested just in these two components. We've looked at sampling and we're going to look at quantization in a minute. Everything else, so all of this, we're going to look at later. So all of this is going to make more sense in the coming lectures. So today I want you simply to focus on that smiley face there. So quantization formally is just a mapping of a discrete time continuous valued signal into a discrete valued signal. We use two things: decision levels and representation levels. So think of it as replacing an analog value with a digital value. So if you were to imagine that we have some values, say 3.2, 4.8, 5.1, and you're approximating these by rounding them to the closest integer, that would give you 3, 5, 5. But these aren't the real values. You've lost something, haven't you? So in this process, you've lost something. What you've lost is the difference. You've lost 0.2 minus 0.2, 0.1. That you will never recover. That is lost forever. That is what we call the quantization error. And if you put that error together, it gives you something that we refer to as the quantization noise. It's the difference between the actual values and the values after you've approximated them. So the error is what we refer to as the quantization noise. Is it the same as the noise we spoke about in the first lecture when we spoke about bandwidth degradation? It isn't. No, this is noise that's very much correlated with the signal. But we refer to it as noise because it's as if you have your actual signal, and then you add this error to it, and that's your digital signal. So it's as if your digital signal is your actual signal after it's been corrupted with some kind of additional signal. We call it noise or quantization noise, but it isn't noise in the strict sense of the word. There's two types of noise, quantizer noise: overload noise and granularity noise. So if you imagine a signal that looks like this, and imagine that we have a quantizer with a number of levels. Let's just say we've got these 6 levels. So the signal will be sampled. I'm not going to illustrate the sampling, but I'll just show you that values can be approximated, but these values can't. Values which exceed the dynamic range. The dynamic range is this range here between the minimum level and the maximum level. That's what we call the dynamic range. of the quantizer. When we talk about a quantizer, actually what we're talking about is our ADC chip. So we have a dynamic range. The dynamic range is that. If you exceed the dynamic range, then you're going to result in clipping. So the bits above and below the dynamic range result in clipping. So this is your noise. What kind of noise? We call it overload noise, because that's when you've actually exceeded the dynamic range. The granularity noise is related to the resolution. It's related to the number of levels. It's related to the spacing of these levels. We'll look at that in a little bit more detail. Quick question. Is it possible to perfectly reconstruct a signal after quantization? So let me illustrate what I mean. Say you have your analog signal and it's sampled. Then after sampling, it's quantized. So that's your ADC. After that, what you have is a digital signal. Now, we've already established that it's possible, after sampling, to recover the original message. That is possible. Okay? The question is it possible to recover the original message after quantization? Or even, is it possible to recover the message after quantization? So we're not necessarily revisiting the question of sampling, because we've already established that. We're interested in this second question. And the answer is no, it's not possible. There is no way to recover this error. So this cannot be recovered. This error cannot be recovered. This is lost forever. The 0.2, 0.2 and 0.1, that is lost forever. We cannot recover that. So the answer to this question is no. It's not possible. So, when we talk about a quantizer, we often refer to something called the bit depth. The bit depth it's another way of saying how many levels do we have. So if you had 16 levels, you would need 4 bits. If you had 8 levels, you need 3 bits. If you have 4 levels, you'd need 2 bits. So in general, the number of levels is a power of 2. So it's 2 to the power n, where n is the number of bits. So n bits, L levels. And another way of writing that is you could say that n is log to the base 2 of L. So you can see clearly if you have the same sample rate, notice the sample rate isn't changing, as you reduce the number of levels, your reconstruction becomes less and less close to the original. So the original is the blue signal, or the samples on the blue line at least. And here you have a much better approximation. So clearly the number of bits, the more the number of bits, the more the number of levels, and the more the number of levels, the better the reconstruction. So how many bits would you need? How many bits? So the question is find n for the number of levels, 24. So n is how much for L is 1024. So remember we said L is 2 to the power n, or n is log L to the base 2. So the answer is you'd need 10 bits. So 2 to the power 10 is 1024. So that's how you would answer that. Similar question here, but in general, if you were to double the number of levels, how many more bits would you need? So remember we said if n is 10, L would be 1024. If L were twice that, so 2048, how many bits would you need? Would you need 20 bits? Would you need 5 bits? Or would you need 11 bits? Now, if you think about it, you'd only need one extra bit. You'd only need one extra bit because you can either say 2 to the power 11 is 2048, or log to the base 2, 2048 equals 11. That's for a specific example. In general, you can do the same, simply because you're adding 1. So you're multiplying by 2, therefore you're adding 1. So you can do that mathematically. You can say something like, if 2 to the power n equals L, then if you have 2L, then you would have 2 to the power n plus 1. So you simply add 1 extra bit to double the number of levels. If you go back to this, here you can see it quite clearly that here we had 8 levels, because remember we have 0, and here we have 16 levels. So to double the number of levels, we simply added 1 to the number of bits. So that was looking at the quantizer. Now we're going to go back just for a second to look at sample rate. So let's assume that we're always oversampling. So oversampling, oversampling, oversampling. But look at the quality of the reconstruction. As you increase the sample rate, the quality of the reconstruction improves. Now, we've said before that if the sampling rate increases, that doesn't improve the quality of the reconstruction for an analog signal. So if fs is 3B or 300B or 3000B, the quality is the same because the quality is simply 100%. So you've recovered it perfectly. So you can't get better than perfect. But because we're quantizing, the sample rate actually does make a little bit of a difference. So as you improve the sampling rate, you actually get a better digital reconstruction. So you have a choice of sometimes increasing the resolution by improving n, and sometimes you improve the quality by increasing the sampling rate. Each of this will have a different effect on your digital communication and your bandwidth and your bit rate, and we'll look at that in more detail in future lectures. The final thing I want to cover today is about non-uniform quantization. A non-uniform quantizer is one where we have fewer or more levels allocated to different ranges or different sections in the dynamic range. So look at this signal here. So we have two sine waves. Let me illustrate this. We have a sine wave of considerable amplitude, and we have another sine wave of lower amplitude. So if this was voice, then this would be a loud sound, loud voice, and here would have a softer voice. Now, it turns out that the human ear is much more sensitive to lower amplitudes. So small variations in amplitude, the human ear picks up very well. But changes in larger amplitudes, the ear is much less sensitive to it. And it's also to do with the probability distribution. So as it happens, there are more lower amplitude variations in audible speech, and the human ear is more sensitive to these. So if we only had 3 bits to use, if we had n equals 3, so L equals 8, we could distribute these 8 levels uniformly, or we could allocate 4 levels to the lower amplitudes and only 4 levels for the remaining higher amplitudes. Now we have a non-uniform quantizer. And if you look at the quality, if you look at the reconstruction here, if you look at, well, it's not the reconstruction, if you look at the digital representation there, that is much different from what you have here. So as it happens, this is a more pleasing sound, it's a higher quality sound, it's a more intelligible sound, it makes more sense, it's easier to understand than something that's quantized uniformly. So we, rather than actually having non-uniform quantizers, we actually often have a linear quantizer flanked on either side by non-linearities. So you'd have a non-linearity, then the inverse, the same non-linearity at the receiver, but in inverse. So this is at the transmitter, and this is at the receiver. And you'd have a non-linearity on either side, and together this compression and expansion we refer to using this made-up word of companding. So companding is like the panding from expansion and the comp from compression. And different countries, so the UK, Europe, Japan, and the US will have different laws, different formulas. By laws, I don't mean regulations, I mean different formulas for this function. So this compression function, you'll have different formulas in different countries, and we often use this for telephone. Why do we do it? It's mostly to improve the quality. It's because the human ear is sensitive or more sensitive to lower amplitudes. So it also has advantages of reducing the buzz and hiss. But it's making better use of the dynamic range without increasing the number of bits. That's important. What we're doing is not increasing the number of levels. So we're increasing the quality, but without increasing the number of levels. Okay, so that was quantization. Now we've finished sampling and quantization and digitization. We're now ready for digital transmission. But there are 2 ways we can carry out digital transmission, either baseband or bandpass. And if you look at these 2 sets of photographs, there are 2 very different things going on. What do we have in common? All of these pictures in common on the left, all of these have in common that there's a cable involved. That's baseband communication. Whereas all the photographs on the left, these are all wireless. These are all radio signals. So these are all bandpass. So these require actual modulation. Whereas here, it's all pulse or cable modulation. So each of these we're going to have lectures about. We're going to have a lecture about baseband modulation and then 2 lectures about wireless or radio modulation, digital transmission. So all of that comes after Easter. That's a summary of what we've done today. We still have one lecture to go here, 2 lectures about digital modulation, and 1 lecture about multiplexing with problem classes in between. And just as a reminder, please put in your diaries 30th of April. April, 9 a.m. That's our next home test. I was about to say class test, but that's our next test. It's on the 30th of April, 9 a.m. So, final words, wherever you are, I hope you're staying at home and you're looking after yourself and you're staying safe. I hope to see you again this year. In case I don't, I will definitely be seeing you all again next year. So stay home and stay safe.